Welcome back to the Deep Dive. Today we are taking what I think is the ultimate shortcut to understanding how the entire global computer network, the thing we all rely on, actually moves data.
Right. We've talked about digital communication, binary bits.
But now we're kind of zooming out, right?
Mm.
From that microscopic view to the actual structure that carries it all.
It really is networking 102. I mean, last time we touched on big ideas like the internet protocol, but that's for talking between networks. Before we can even get there, you absolutely have to understand the rigid structural rules that let all those billions of bits travel.
Across the wires, through the air, every single second.
Exactly.
And the map we're using for this whole journey it's the foundational standard, the Open System Interconnection Model, the OSI model.
Right. And let's break that down because it's a conceptual framework. It's not a physical thing. It's a model with 7 distinct layers.
Yeah.
Each one has a very specialized job.
What's so amazing to me is how modular it is.
It is. Each layer kind of does its own thing. It defines specific protocols, rules and standards for how software and hardware talk at that level. This is why a computer from one company on one operating system can talk to a server built by someone completely different, halfway across the world.
Okay, so since we're going to be living in these layers for a bit, we have to give you the memory tool. It's the mnemonic that every network engineer basically has tattooed on their brain. It helps you remember the layers 7 down to 1.
It's a little juvenile, maybe a bit absurd, but trust us, you will never, ever forget it. Please do not throw a sausage pizza away.
Please do not throw a sausage pizza away. That's the key. So for today, our mission is to focus just on layers 1 and 2.
The physical layer and the data link layer, the absolute foundation.
Let's start right at the bottom then, layer 1. I mean, when you strip away all the software, all the addressing, what is the most basic, fundamental element of moving data?
That is layer 1. It's the physical channel. This layer defines the medium itself. We're talking about the physical specs that allow raw bits, ones, and zeros as, energy to move between systems.
But this is the stuff we can actually touch, right? The wires.
Exactly. When we say layer 1, we mean fiber optic cable, which sends pulses of light. We mean twisted pair copper, which is sending electrical signals, usually voltage differences. And of course, wireless, where data travels on radio frequencies. Layer 1 is the cabling, the connectors, the voltage, all of it.
Okay, so if I plug a cable into my laptop, layer 1 is what's responsible for making sure that signal is clean and just gets the bits across. But you mentioned something interesting. Layer 1 is often described as apathetic. What does that mean?
That's such a crucial insight into the design. Layer 1 does not care about the data passing through it. Its only job is to get a voltage change or a light pulse from point A to point B. It has no idea if those bits are a cat video or your bank password.
Why is that so important? Why build it that way?
Modularity, resilience. If layer 1 had to know what the data was, it would have to change every time data formats change. But since it only cares about electricity or light, you can upgrade your whole network from copper to fiber, and the layers above it, the addressing, the applications, they don't have to change at all.
It's just a dumb, reliable pipe.
It's a dumb, reliable pipe. Its job is to keep the lights on and the signal moving. That's it.
Okay, that makes perfect sense.
Yeah.
We have the pipe. But for those bits to actually mean anything, they need a destination. They need some intelligence. And that takes us right up to layer 2.
The data link layer. And this is where every single network-capable device introduces itself. It does that with the network interface card, the NIC.
The NIC.
Yeah, it's a circuit board or chip. It's the gateway between your computer and the network. Wired or wireless, and the NIC is your physical connection point.
And if it's the layer of destination, that NIC has to have some kind of unique ID, a calling card.
It does, and this is one of the most important concepts. The Media Access Control Address. The MEC address. This is the device's unique physical identifier. It works like a house address, but only within a single local neighborhood.
We know it's an address, but what makes up MEC address so different from, say, an IP address or any other address we use online?
The word physical is everything. It's a 48-bit value, so 48 ones and zeros long. And critically, this address is literally imprinted on the NIC circuit board when it's made.
So it's permanent.
It is a permanent fixed identifier.
48 ones and zeros. That sounds like a nightmare to try and read. How do we actually see it?
Well, to make that manageable for humans, it's represented in hexadecimal notation. It just so happens that 4 binary bits translate perfectly into 1 hexadecimal character. So a 48-bit address becomes just 12 hex characters.
It's just a more compressed, readable format.
Exactly.
It's hard to wrap your head around the global coordination needed to make sure that no 2 devices made anywhere on Earth ever have the same 48-bit number. How does that even work?
That's where organizations like the IEE come in. A manufacturer, say Intel or Broadcom, has to literally check in with the IE and request a block of MAXI addresses. The address itself is actually split in half just for this reason.
Oh, interesting. Tell us about that structure.
So the 12 hex characters are divided into two parts of 6. The first 6 characters are the OUI.
Organizationally unique identifier.
Right. And that identifies the manufacturer. So you can look at the first half of any MSC address and know who made that network card. The other 6 digits are the device ID, which the manufacturer assigns uniquely to that one card.
So the OUI is like the postal code.
Yeah.
It tells you the region, or in this case, the company, and the device ID is the actual street address.
That's a brilliant analogy. It scales incredibly well. You know who made it, and you know its unique serial number from that maker.
Hold on. If this address is physically burned onto the chip, can it be faked? Can someone clone or spoof a physical address?
That's a great question, and it gets into network security. So while the AMC address is designed to be permanent, a skilled user can tell their operating system to pretend to have a different MFC address, to spoof it. But the underlying physical address on the hardware never changes. And for local communication, the network hardware relies on that integrity.
Okay, so we have the unique physical address, the MPC address. Now, how does Layer 2 use that to actually package and move data?
This brings us to frames.
Frames.
When your computer's operating system wants to send something, a piece of a website, a chunk of a video file, it hands that data down to the NIC. And the NIC's job is to break it all down into these little movable containers called frames.
So the NIC is constantly building, sending, receiving, and then taking apart these frames.
All day long. And the structure of that frame is very strict. It's got 3 main parts. First is the header, and the header is critical. It contains the recipient's MAC address, the sender's MAC address, and the type.
The type as in what kind of information is inside? Is it web data? Is this something else?
Precisely. After the header, you get the payload. That's the actual data you want to send. And then at the very end, you have the trailer. And the trailer contains the FCS, or frame check sequence.
Frame check sequence.
Yeah, and this is more than just a simple check. It's a mathematical checksum. It uses some pretty sophisticated binary math to verify that the frame arrived correctly and wasn't corrupted by static or signal loss on the wire.
So Layer 2 is the first layer where we see intelligence that's actually checking for data integrity.
Absolutely. But, frames can't be infinitely large. There's a size limit.
Right. What's that like?
Typically, it's constrained to 1,500 bytes.
It's not very much.
It's not. And that's partly for historical reasons, to make sure no single device could hog the line for too long. So if you're sending a giant file, your computer's OS chops it up into thousands of these little 1,500 byte frames, and the computer on the other end patiently puts them all back together.
That is a staggering amount of work happening all the time. Okay, so we need the final piece of the Layer 2 puzzle. The hardware that directs all this local traffic. Let's talk about the switch.
The switch. It's the central traffic controller for a local area network, a LAN. Its main job is to connect all the hosts, all the computers, printers, everything, and make sure that frames only go to their intended destination, not to everybody.
So how does a switch know where every single device is? It has to have some kind of internal map, right?
It does. It's called a NAC address table. And the switch builds this map, this memory, every time a new device connects. The mechanism it uses to learn all this is the Address Resolution Protocol.
ARP.
ARP. It's brilliant.
Okay, let's walk through it. Say host A wants to talk to host C, but A has no idea what C's MAI address is. What happens?
Host A starts by sending out an ARP request, but because it doesn't know where C is, it can't send a direct message. It has to be a broadcast.
A broadcast.
Yeah.
So it sends it to everyone.
To everyone. The switch is like a big open plan office. The ARP request is like host A standing on a chair and shouting, "Hey, I need to talk to the person at IP address 192.168.1 feet.
Yeah.
Who are you and where are you sitting?"
And the switch makes sure that shout goes out to every single desk.
Every single one. It seems inefficient, but it's just for that one initial moment.
Okay.
Because only the matching host, only host C is going to respond. And when host C replies, it doesn't shout back. It sends a unicast ARP reply, a private message, directly back to host A. It says, "Hey, I'm 192.168.150, and my MAC address is XYZ. I'm right here."
That is so cool. So what would happen without ARP?
Chaos. Every single data frame would have to be broadcast. The network would be just constant noise. It would grind to a halt. ARP makes sure that after that first shout, all future communication is direct, point-to-point and super efficient.
And the switch is listening to all this. It updates its own MSE address table.
It does, but
Yeah.
that memory doesn't last forever. No, switches are designed to clear out old entries after a few minutes or hours of inactivity. This keeps the table clean and accurate, in case a device gets unplugged or moves to a different port.
So that really brings the whole layer 2 loop together.
Mm-hmm.
The OS passes data down, the NIC builds the frame, adds the ME addresses, the error check. The frame travels over the physical wire layer 1 to a switch. The switch checks its table, sends the frame to the right port, and the destination NIC grabs it, unwraps it, and hands the clean data up to the OS on the other side.
It's a miracle of precision just to move one chunk of data across one room.
It really is the unseen engine of everything we do online.
It is. So let's just quickly summarize what we've covered in this deep dive. We started with the OSI model, its 7-layer structure.
Layer 1, the physical layer. The
Yeah.
simple, honest medium. Copper, fiber, wireless. It's the highway, but it doesn't read the billboards.
Right. And then layer 2, the data link layer, which is where the intelligence starts. It's the layer of physical addressing with that unique permanent MAC address burned onto the NIC.
And it handles framing the data into those 1,500-byte chunks and managing local traffic with switches and that elegant ARP protocol.
Perfect summary.
And of course, everyone, remember the tool. Please do not throw sausage pizza away. Use it.
This sets up the central conflict for our next deep dives. We spent all this time talking about the MAC address. It's permanent, it's physical, it's essential for talking on your local network. But
Right.
what happens when data needs to leave your local network? What happens when you go from your house to a coffee shop? Your MA address, your physical address, hasn't changed.
But you need to talk to a server on the other side of the planet.
Exactly. The global internet needs an address that is not fixed to the hardware. An address that's logical, transient, and can cross network borders.
And that conflict between the permanent MAC and the logical global IP address, that's exactly what we're going to dive into next time when we get to layer 3.
But until then,
Yeah.
just think about the phenomenal quiet complexity happening every single time you open a browser. It is truly amazing.